In this video, I will go over the homework that follows the lecture 0.5.2 called the Fundamental Theorem of Calculus, and let's just jump right into it. I expect there will be a few problems asking us to use either the first or the second statement of the Fundamental Theorem of Calculus. As always, I hope you did watch the brief review of the content, so that will help me and you to have more efficient communication. In this case, let's start with the first problem. So we're looking for the derivative of a function defined as an integral with a variable in one of the boundaries, and because it's in the bottom, we're first going to use the property and switch the limits, because the fundamental theorem of calculus only tells us what to do when the variable of differentiation is in the upper bound. Now we can differentiate this function. So to find the derivative, we have to differentiate this, or we have to differentiate this. And according to the fundamental theorem of calculus, it is simply the integrand evaluated at the upper limit, which is our variable. And that's it. If here we had another function, let's say g of x, then we would have multiplied by g prime of x after plugging in g of x into the function, but we only have x, so we got the answer. The answer is negative square root of 2x minus 2. In this case, we already have x in the upper bound, so the derivative of this function is simply the integrand evaluated at x. That's it. So I'm just going to copy it right there. This is the combination of the fundamental theorem of calculus and the chain rule. So when the function in the limit is not just x but some function, what we do according to the fundamental theorem of calculus is we plug in that function into the integrand and then multiply by the derivative. So in our case it will be 3x squared divided by 3x squared minus 1, and we're going to multiply by derivative of 3x squared, which is 6x. Let's do the next problem. Same thing, so we're going to plug in the limit into the integrand instead of the variable, and then we're going to multiply by the derivative of the limit. When the limit is just a variable, it's as simple as plugging in that variable into the integrand. And here we have to multiply by the derivative of the that function. So waiting for this message to go away so we can move on to the next question. Okay, so this is the second part of the second statement of the Fundamental Theorem of Calculus that we use to find the definite integrals analytically without graphing the function and looking for its net signed area. So the first step is, and again, to summarize it, the integral from a to b of f of x dx is equal to the antiderivative evaluated at b and minus the evaluation at a. So this is how we express it symbolically. So the first step is to find the antiderivative. So the antiderivative in this case is, it's going to be 2 over 15x to the 5 minus 3 over 8x to the 4 plus 5 over 8x squared minus 1/3 x. And now we're going to plug in 0 and 2. And first we're going to plug in 2. So 2 15ths times 2 to the 5 minus 3 8ths times 2 to the 4 plus 5 8ths times 2 squared minus 1/3 times 2. And we're going to now subtract the same thing but evaluate it at 0. But notice how if we plug in 0, we get 0. So the final answer is 2 to the power 6, 64 over 15, minus 2 to the power 4, 16, so over 8 is 2. We have 5 halves minus 2/3. So I don't know about you, but I would honestly prefer to plug this into Desmos, or even just plug it like this into the answer box in Newton, but I'm certainly not interested in computing this by hand. Let's see what's the answer. Oh no, what a nice answer, 0.1. How much time we saved by using Desmos now instead of doing it by hand. That's the time that we can spend doing other things other than calculus. Alright, next question. Another application of the Fundamental Theorem of Calculus. So again, step 1, find the antiderivative. Step 2, evaluate the antiderivative at both boundaries and find the difference. So first, antiderivative, negative 2 cosine x plus 2 sine x from 0 to power over 3. Be careful here because not all functions at 0 are 0. Last time we had a polynomial without a free coefficient, but this time we have a trig function, and like I said, not all trig functions at 0 are equal to 0. Remember that. The cosine of pi over 3 is negative, sorry, it's just 1/2. Sine of pi over 3, it's root 3 over 2. This is plus 2. Cosine of 0 is 1, and sine of 0 is 0. So the final answer is negative 1 plus over 3 plus 2. So the answer is 1 plus radical 3. Interesting. So let's see what the question is asking us. First of all, we have to find derivative of g and evaluate it at 8. So to find the derivative of g, we're going to differentiate this integral function with respect to x. And according to the fundamental theorem of calculus, it's simply f of x. And now to evaluate g prime of 8, or at 8, we have to plug in 8 into f. And f of 8 is equal to 0. So the answer is 0. Interesting, not a trivial question here, so let's take a look. F is the function whose graph is shown below. G of x defined as a cumulative area function, and to understand what that means, let me bring this image here and let's play with it. If a is some number between -8 and 8, let's say this is my a. So this function integral from a to x of f of t dt represents the area from here to whatever x is under the graph of this function. So you see how when the area is positive, x will be increasing because you keep adding positive area. But as soon as you cross this point and the area becomes negative, x getting larger will result in decreasing the cumulative area because of the negative sign. So the answer is it's increasing from -8 all the way to 3. This is, we've done a problem like this before when we only had to do the indefinite integral. Now we're going to do the whole thing. First step is to simplify the integrand. So we have 4x squared minus 2, and we have -4x plus 2x, so it's just -2x. And we have to guess now the antiderivative, so it's going to be 4/3 x cubed minus x squared minus 2x. That's the antiderivative, and we evaluate it from -4 to -1. So we plug in -1 and then subtract the same, but evaluate it at 4. So 4/3 4 cubed minus 4 squared minus 2 times 4. And this is -4/3 minus 1 plus 2 minus, and here we have a lot of 4's. So 4 cubed is what? 64. 64 times 4 is 256 divided by 3 minus 16 minus 8. But we distribute this negative, so it becomes plus plus. So what do we have? We have -260 over 3 plus 1 plus 16 plus 8 is 25. So it's pretty much negative 260 plus 75. So negative 185 over 3. Hopefully I didn't make a computational mistake. If I did, then we'll redo the problem. Great. So let's check the work. First of all, did I distribute it correctly? I'm going to use Wolfram Alpha for that. 2 minus 2x times negative 2x minus 1. Hopefully. Let's see. 4x squared minus 2x minus 2. I did distribute it correctly. I see what I did wrong. Should have plugged in negative 4, not just 4. So plugging in negative 4 changes the sign here. Changes the sign here as well. So now we have negative 4 plus 256, that's 252 over 3. Minus 1 plus 2, 17 minus 8 plus 9. And 252 is divisible by 3. That's 84. And 84 plus 9 is 93. Now, this time, because I don't want to risk it, I'm actually going to check my also final answer with Desmos here. So I'm going to type this integral, negative 4, negative 1, 4x squared minus 2x minus 2 dx. The answer is 93. That's right. So now I'm more confident. Excellent. At this point, it could be very tempting to just put this problem in Desmos. We are going to resist that temptation because you are only allowed to do pre-calculus problems with technology. In this case, we're going to find the antiderivative first. The antiderivative is negative 3 tangent x minus 1/3 x cubed, and we're going to evaluate it from negative pi over 3 to pi over 3. And I have I don't have a feeling. I was just going to use the fact that this function is even, but it doesn't matter. Still have to compute it. So negative 3 tangent of pi over 3 minus 1/3 pi over 3 cubed. That's on one hand. And on the other hand, we subtract the same, but evaluate it at negative pi over 3. So tangent of pi over 3 is sine of pi over 3 root 3. Cosine of pi over 3 is 1/2. So root 3 over 2, so it's root 3 minus pi cube over 81 plus tangent of negative pi over 3, which is going to be negative root 3. And here we have minus minus plus, but we have another minus, so it's going to be another pi cube over 81. So the final answer is negative 6 rad 3 minus 2 pi cube over 81. All right, 2/3 done. Let's find antiderivative first. Negative 3/5 x to the power 5 plus x to the power 4 minus 3/2 x squared plus 3x, and we evaluate it at negative 3 and negative 2. So first plug in negative 2, negative 32 plus 16 minus 3/2 times 4 minus 6. That's us evaluating it at negative 2. And minus, now we plug in negative 3. So we have negative 3/5, negative 3 to the power 5 plus 81 minus 3/2 times 9 minus minus 9. And let's try our best to simplify this. We have 96 over 5 plus 16 minus 6 minus 6, so it's plus 4. That's what's left of the first parenthesis. In the second parenthesis, we have this crazy 3 to the power 6 over 5 plus 81 minus 9. That's the same as 72, and we have minus 27 over 2. And I'm not doing this by hand, so let's just use decimals. 96 over 5 plus 4 minus 3 to the power 6 divided by 5 plus actually minus 72 and plus 27 over 2. The answer is negative 181.1. Negative 181.1. Let's see if it works. And of course it does. We've done a problem like this before, so it shouldn't be a problem, right? So we're going to first distribute everything. So we have negative 4x squared minus 3, and the x term is 6x plus 2x, so it's plus 8x. Now we're going to find the antiderivative, so negative 4/3 x cubed plus 4x squared minus 3x, evaluated from negative 1 to 0. When you plug in 0, you get 0, and we subtract the value obtained from evaluating it at 1. So we end up with negative 4/3 minus 4 minus 3. So negative 4 minus 7 times 3, 21 over 3. So negative 25 over 3. That would be my guess. We've done a problem like this before, so right away let's just evaluate it. So negative 2 tangent x minus 5 sine x evaluated at pi over 4 and pi over 3. So negative 2 tangent pi over 3 minus 5 sine of pi over 3. So here, the most important aspect is not to lose any signs. So tangent of pi over 3 is sine of pi over 3, which is root 3 over 2, divided by cosine of pi over 3, which is 1/2. So that's tangent. Sine of pi over 3, as I said earlier, is root 3 over 2, plus 2 tangent of pi over 4, that's just 1, and plus 5 sine of pi over 4, that's root 2 over 2. And I think we don't need to try and simplify this. We have negative 2, so negative 9 square root of 3 over 2, if we collect all the radicals of 3 plus 2, and plus 5 square root of 2 over 2. Another very similar problem. Let's just jump and find the antiderivative. It's going to be 3 secant tangent. Is it derivative of secant tangent? So 3 secant x plus 2 sine x evaluated again at pi over 4 and pi over 3. So secant of pi over 3 is, let's just write this out first, then we'll evaluate it. So secant of pi over 3, it's cosine of pi over 3 is 1/2, so secant is 2. Sine of pi over 3 is root 3 over 2. Secant of pi over 4 is root 2. And sine of pi over 4 is root 2 over 2. So the final answer is 6 plus radical 3 minus 2 radical 2. Pretty nice answer. I guess the only thing I'm not sure here about is what's the derivative of secant, and let's check. Derivative of secant is tangent secant, so that's fine. So 3 secant plus 2 sine. Secant of pi over 3 is reciprocal of cosine of pi over 3, which is 2. Sine of pi over 3, it's root 3 over 2. Secant of pi over 4 is root 2. Why is this minus over here? So this should be minus. So this should be 4. we've seen the problem like this before. So the net area function is just the cumulative area on the given interval. So here we have an interval from 0 to -6 of f of t dt, but the intervals only make sense when the lower bound is at the bottom, so we're gonna flip it first. And now this is the area from -6 to 0. From -6 to 0, let's copy this image over here. From -6 to 0, what do we have here? We have a 4x4 rectangle, and we have 1/2 times 2 times height, which is 4, the area of a square. So we have +16 plus 4, so the total area is 20, but because the sign is negative, so we put -20. So it's like if you're going through the positive area but in the negative direction, you're going to end up with the negative integral. That's what this represents. At what value of x does g of x has a maximum value? That's a good question. It's going to have the it's probably going to have the maximum value when from 0. So if we integrate from 0 to the left, we're going to get negative value. If we go integrate from 0 to the right, we have this positive area and this negative area. So if we start from 0, this is my only positive area, this is all negative area. So we're going to maximize the area if we integrate from 0 only to 2. That's how you can maximize the area. So I would say the answer is 2. And we are done with this homework. So if you have any questions, please let me know.